students, class 10. I welcome you to our channel Mind Mapping. Let's recall. In our last class, we discussed image formation by a plane mirror. Today, we have taken an interesting, a concept-based topic from the chapter Light, that is reflection and refraction, prescribed for class 10. What the topic? The topic is spherical mirrors, structures and features. So let's start. Now look at two figures. You see MN is a part of a curve. Now you see the curve line and a curved surface. It has two surfaces. One is inside. Look at my palm. Now it is a curved surface, and this is called inward surface, and this is outward surface. So this has the MN curved surface has two surfaces, inward surface and outer surface. And here this is inward surface and this is outer surface. Okay. So this MN is a part of a sphere. So if it is a part of a sphere, it has a center. So you see the center. Here, see the center that is behind the mirror. Okay, we shall discuss. Now you see, when that is inward surface acts as a mirror, or inward surface is a reflecting surface, it is called a concave mirror. And when the outer surface acts as the reflecting surface and the inward surface is opaque, that type of mirror is known as convex mirror. And in both the cases you see MN, they are the parts of a sphere. Now you see MN, the part of a sphere, and it has a center. You see, we have marked as capital C. For your better understanding, we have drawn a diagram here. That is, we have drawn a diagram hemisphere, not sphere, because you can easily understand. So now you see, this is the center, and this is the radius of this hemisphere. Now you see, so the point P is the midpoint or the center of the mirror, that is MN, that is P, is called pole of the mirror, that is P. And here P is the midpoint of MN curved surface. Okay. So P is a point that lies in the mirror. So P is a part of the mirror. Now you see, C is inside the sphere. So C is not a part of the mirror in both the cases you see. But here C behind the mirror, and here C in front of the mirror. Okay. So PC distance, you see PC distance is called radius of curvature. So PC is denoted by a symbol capital R, that is radius of curvature. So C is the center, denoted by capital C. Okay, but C is not a part of the mirror, but P is a part of the mirror. So let us join PC. So PC is equal to the radius of curvature. Okay. Now you see PC is the radius of the curvature. Okay. Now look at, if we extend PC, so make a straight line. So this PC straight line is known as the principal axis of the mirror. This is very important. And you see this principal axis PC is otherwise called normal to the point at P of the mirror. So you see, it is normal at point P. What is normal? If it is perpendicular and perpendicular to this point, and if the incident ray after reflection returns back along the same path. So please remember, both two mirrors, they follow the laws of reflection that we have already discussed. Now come to, so we got actually one point P and point C. Now look at, here you see, we have taken an example to explain, that is what we have written, aperture. You see, as per your book, in all cases, the linear aperture, the distance between M and N is called linear aperture because it is an arc and part of a circle, and Mn is less than the radius or radius of curvature. So if it is the case, so the mirror is too small for that aperture, and this is called angular aperture, and this is called linear aperture. So linear aperture is less than the angular aperture. So for that case, there is a relationship between P, C and another point A. Let us find out. Look at this case. The incident rays parallel to the principal axis after reflection, after reflection, they intersect the principal axis at a point that is called principal focus. Here you see the incident ray reflected, and here the incident ray, the point of reflection, point of incidence, and reflected ray, and this point is known as principal focus. And CD is equal to PC, so CD is just called radius of curvature. But you see, we find some deviations here because F is here in front of the mirror. So this focus, the principal focus, is real. Okay, now come to this side. So here F is behind the mirror. Why it is, and it is called virtual. Why do we call it virtual? Look at this. So here the outer surface acts as the reflective surface. So the rays parallel to the principal axis after reflection, you see, after reflection, they appear to have come from a point on the principal axis, and this point is called focus. Since it appears to have come from a point, the focus is not real here, the focus is virtual. So now we got 3 points P, C and F. You see, when the aperture is small than the radius of curvature, then the mirror is small. And if it is the case, there is a relationship among P, C, F. We have got P, C, P for pole, C for center, and F for principal focus, or usually call it focus. Now look at PF, and F is the midpoint of PC, and the PF from pole to focus, the distance is called focal length, denoted by a symbol small f. Now look at here, and here focus is real, but in case of convex, the focus here the focus is virtual that we discussed. So let's establish the relationship among P, C, and F. And F is the midpoint of PC, and PC is the radius of curvature denoted by a symbol capital R. So PC is equal to R. Then we can write PF. PF is equal to FC is equal to focal length. So simply we can write PC is equal to A plus F. So A plus F is equal to twice F. So PC distance, that is radius of curvature, is equal to twice of the focal length. Now by transposition we can derive the focal length is equal to radius of curvature R by 2. These are some key concepts of the topic spherical mirrors, structures and features. Hope you have understood the basic concepts, the key concepts. In our next session, in our next class, we shall discuss the ray diagrams in both the cases, in concave mirror and convex mirror, so that it will be easy to know how the images are formed by a concave mirror and a convex mirror. Please stay tuned to watch our videos. Thank you for watching.